This lesson is about isosceles triangles. So, an isosceles triangle is any triangle with two congruent sides. So let's say in this triangle we have these two sides congruent. Well, then it turns out that the angles that are opposite those sides, so this angle here and this angle here, are also congruent to each other. Okay, notice there's something about the spelling of isosceles, because this is something students have trouble with. It's S-O-S and then a C. So I always think of it as you send out an SOS before you sink in a ship at sea. So, or if you're in trouble at sea. So that's how I remember it. So basically it works both ways. If you have a triangle with two congruent sides, the angles opposite those sides are congruent. If you have a triangle with two congruent angles, then the sides opposite those angles are congruent to each other. And that's basically the isosceles triangle theorem and its converse. In an isosceles triangle, the angle that's included between the two congruent sides is called the vertex angle. And the two congruent angles that are opposite the congruent sides are both called the base angles. With respect to the sides of an isosceles triangle, the two congruent sides are both the legs of the triangle. We call those the legs. And the side that's included between the two congruent angles that's opposite the vertex angle is called the base. So the isosceles triangle theorem is that if two sides of a triangle are congruent, the angles opposite those sides are congruent, and vice versa. The corollaries to that follow logically, the first one is that an equilateral triangle is also equiangular, meaning that if it's equiangular, it's also equilateral, and it has three 60-degree angles. That's the first corollary. The second corollary has to do with if we take a segment straight down the middle of the vertex angle, and we bisect that angle. So if I come down and I bisect the vertex angle, a couple things happen. First of all, I always hit the base at a 90-degree angle, and I hit it at its midpoint. So these two segments are equal. So if I label that bisector AX, segment AX, I can see that a couple things here. I'll have segment BX will be congruent to segment XC because X is the midpoint. I can see that I've got 90-degree angles, so angle AXB and angle AXC are both equal to 90 degrees. And in the third thing, I can see that what I've done is I've bisected that angle, so angle 1 congruent to angle 2. Basically, I've divided the isosceles triangle into two congruent back-to-back right triangles. So here's for a few warm-up exercises. If I'm supposed to find the value of x, I'm looking at an isosceles triangle, and I see that one of the base angles is 50 degrees, and I know that that has to be congruent to the other base angle of 50. So together those add to 100, and I know to finish off the triangle at 180 degrees that the x has to be equal to 80 degrees. In a second example, I have an isosceles right triangle where you can see that the vertex angle is a 90-degree angle, and I know the other two have to be complementary. They have to add to 90, and I know that because I have two congruent sides, that these two base angles must be congruent to each other, so they would each have to equal 45 degrees. In this next example, we have an isosceles triangle because I see that I have two angles that are congruent to each other, so I know that the sides opposite those angles must be congruent to each other. So to find the value of x, I know that the side that's labeled 2x minus 4, that the value or the length of that side has to be equal to the same as the side labeled x plus 5. So then solving for x, we get that x equals 9. And that would mean that this side 2x minus 4 is 2 times 9 minus 4, or a length of 14. And this side would be 9 plus 5, this congruent side, which would be 14. And if we had to find the base, it would be 2 times 9 plus 2, so 18 plus 2, or 20. In this next example, we have to find x, and x is the length of one of the sides. And we don't really know if this is an isosceles triangle yet until we find out what the missing angle is. So if I add up the two angles that I know, of 56 and the 62, those two have a sum of 118. So if I subtract that from 180, I can see that the remaining angle, the angle that is not labeled, is 62 degrees. So if this angle is 62, now I see that it's the same as the other 62 degree angle. So these would be two base angles of an isosceles triangle, and the sides opposite those angles must be congruent. So this side here and this side here. So that means that x must equal 42, the same as the length of the other congruent marked side. Okay, let's look at a simple proof that uses the isosceles triangle theorem concept. First of all, we have a figure where we're told that, given that m is the midpoint of jk. So what that means is that jm, this piece here, is congruent to mk. So jm is congruent to mk. Now, what I'm asked to prove is that jg is congruent to mk. I've already got jm congruent to mk, so if I can link jg and jm, then I'm in luck. Okay, so this was the reason that jm and mk were congruent is midpoint definition. Okay, and then from there, I'm given that angle 1 and angle 2 are congruent. So I know that if they're congruent, that the sides opposite those angles are congruent. So I know now that jm and jg must be the same length. So jm is congruent to jg, and that is the isosceles triangle theorem. That if I have two congruent angles in a triangle, then the sides opposite those angles are congruent. It's actually the converse of the isosceles triangle theorem, but we'll look at the theorem and its converse as one. So then lastly, I have if jm is congruent to mk and jm is congruent to jg, then these two, mk and jg, must be congruent to each other by substitution, or the transitive property. So that's it for isosceles triangles. They're really pretty easy.